Okay. All right, I'm going to go ahead and get started. Okay, I'm going to start off by showing a YouTube video. Okay, this is potassium permanganate and glycerol or glycerin.
I approve this message because in the U.S. Senate, my mission will be to bring down the cost of health care.
Okay, this is potassium permanganate. It's a dark purple solid. And okay, that's glycerin or glycerol. That's 1,2,3 propane triol. They're just mixing the two substances. Okay, it takes a few minutes to get started, so this is a time lapse. Okay, adding some more. Okay, and then here it goes. Okay, so my point here is we have KMNO4. Potassium permanganate. Okay, plus glycerol. And we get fire. Okay. Last time we looked at picking an alkyl benzene. Okay, we'll start with toluene. Rather than solid, this is usually aqueous. It's aqueous in its basic solution, and this is heated. Okay, we get benzoic acid. So my point here is that, as you saw from the video, potassium permanganate is powerful stuff. It's a powerful oxidizer. And yet, if we oxidize an alkyl benzene, okay, notice the benzene ring remains intact. It's exceptionally stable. It's resistant even to potassium permanganate. Okay, if we have some other chain, okay, say we have propylbenzene or isopropylbenzene, we still get benzoic acid. Okay, everything gets chopped off except that last carbon, and it gets oxidized all the way to a carboxylic acid. Okay, so it doesn't matter if that chain is 100 carbons long. The only requirement is that we have to have at least one H. We have to have at least one H at this, what is called the benzylic position. Okay, so terbutyl benzene would not, would not result in oxidation of the side chain. In fact, you would start to get oxidation of the ring. Okay, so benzene ring is exceptionally stable, and this is reflected in its reactions. Okay, benzene, okay, let me admit someone else here. Okay. All right, the benzene ring is exceptionally stable. This is reflected in its reactions. Benzene and its derivatives will tend to undergo substitution, okay, rather than addition. The benzene ring is preserved. Okay, before we look at the PowerPoint, I want to do a review of benzene and derivatives nomenclature. Okay, these are referred to as ortho, meta, and para. For di-substituted benzenes. Many of these designations still exist commercially in the United States. We did an extraction lab in which we used p-nitroaniline, although the IUPAC is actually 4-nitroaniline. These terms are still used to specify relative positions. Okay, we say this substituent is ortho to that one, or it's meta to that one. Okay, it's 1,3 or 1,2. Right, many monosubstituted benzenes have common names that have been so widely used that they're accepted by the IUPAC. Okay, this one is toluene, aminobenzene, aniline, phenol. Okay, phenol is also a name for a functional group, but with just one OH, that's called phenol. Okay, some others. This is benzoic acid. Okay, the strict IUPAC name would be benzene carboxylic acid, but this is so commonly used. Styrene, vinyl benzene. And then there are several others. This is benzaldehyde. Aldehyde. Okay, if we have other substituents on here, phenol or benzene, or toluene or phenol, or say I said phenol already, or benzoic acid, if that's the parent compound, then the major substituent's automatically on number 1. Okay, so this would be 3-bromo benzoic acid, for example. 3-bromo benzoic acid. All right, if we have 2 or 3 or more substituents, okay, we want to try to give them the lowest possible set of numbers. Okay, for example, we have this. Okay, parent compound is phenol. Phenol takes precedence over toluene or xylene. Okay, so that means the OH is automatically on number 1. And the other groups, we want to give the lowest possible number. So we wouldn't go around this way, we'd go around this way. So this would be 3,4-dimethylphenol. 3,4-dimethylphenol. When a benzene ring is used as a substituent, then it's a phenyl. Okay, so for example, in this case, it would make more sense to call the cyclopentane the parent, since it's more substituted. Okay, so this would be 1,3-diphenyl cyclopentane. Okay, don't confuse phenyl with phenol. Phenyl does not have an OH, phenol does. Okay, so that's 1,3-diphenyl cyclopentane. Okay, that's distinctly different from benzyl. Okay, this is a benzyl substituent. Okay, it seems like a benzene ring should be a benzyl, but actually this is a benzyl. And this is referred to as the benzylic carbon. Okay, we also looked at some heterocycles. Okay, in which one or more of the carbon atoms is replaced with some other element. Okay, this one is called pyridine. This is pyrrole or pyrrole, and furan, and then the sulfur analog, the thiopene. Okay, aromatic compounds have certain characteristics. Okay, first of all, they have to be cyclic, but not everything that's cyclic is going to be aromatic. Okay, that's the first requirement. It has to be as planar as possible. It has to have a certain number of conjugated pi electrons, either 2, 6, 10, 14, and so on. 2n plus 2, or n is a positive integer, or 0. Okay, so if we were to remove any one of those double bonds, this would no longer be aromatic. Okay, it would just behave like an alkene. All right, let me go to the PowerPoint. This will be chapter 9. Okay, there we go. Maybe. Okay, let me try that again. Oh, there it is. Okay. Okay, so I said at the beginning, the benzene ring is exceptionally stable. There's no ring strain. There's continuous delocalization of electrons all the way around the ring. Okay, we don't have isolated double bonds and single bonds. Instead, the electrons are completely delocalized. And this gives rise to what is called resonance energy. And so the stability of benzene is greater than what we would predict from a 6-membered ring with 3 alkene groups. Okay, you can see that it's significantly harder to reduce benzene to cyclohexane. Okay, it requires tremendous pressures, also high temperatures over 100 degrees in order to accomplish this. Okay, here are some polycyclic aromatic hydrocarbons. Okay, we'll see those again. Once again, you have to have a 1,2p atomic orbital on each atom of the ring. Okay, and that's what we have here. We have to have, it has to be planar and nearly planar, and it has to have a certain number of pi electrons. Okay, so the number of conjugated pi electrons would be divisible by 4 with 2 left over. Okay, and benzene meets these criteria. Here's pyridine and pyrimidine. With pyridine, we don't count the lone pair of electrons on the nitrogen because it's not overlapping with the aromatic system, but pyridine is still aromatic. Okay, this is furan. Furan has 2 pairs on the oxygen. Okay, 1 pair we count. Okay, so we have 6 overlapping pi electrons. This this pair is not in a pi orbital, so we don't count it when we're determining whether it's aromatic. So furan is aromatic. We count the pair of electrons on pyrrole. Okay, here's some other aromatics. These are some polynuclear aromatic hydrocarbons where we have benzene rings that are fused to each other. Benzoapyrene, as I mentioned, was and is a potent carcinogen. We can oxidize a side chain with permanganate or chromic acid. That gives us benzoic acid. Okay, and it's not just methyl, it's any alkyl side chain, as long as there's at least one hydrogen on this position. Okay, notice the nitro group and the chlorine are not oxidized. Okay, if we have more than one side chain, they both get oxidized. Okay. The most common mechanism for aromatic compounds is what's called electrophilic aromatic substitution. Okay, and once you recognize this pattern, okay, you've got most of the reactions figured out. Okay, so we have some kind of electrophile. Okay, the details are often in what the electrophile is and how we generate it. Okay, but once we've got the electrophile, okay, the benzene ring is electron rich. It reaches out and attacks. Okay, and these substitution reactions will have this common intermediate. It's just a matter of what the identity of the electrophile is. Benzene ring is exceptionally stable, so we don't want to disrupt the benzene ring. So instead, we want to restore it. So a base come along. It doesn't have to be a very strong base. Base will remove that hydrogen. This pair of electrons will then move toward the positive charge. Then we get back our benzene ring. And then the base carries away the hydrogen. Okay, so this is the general pattern. It applies to most of the reactions, not all of them, but most of the reactions in this chapter. Okay, so here we have chlorination and nitration. Both of these require a catalyst. Okay, so here we're using chlorine gas. If we mix benzene and chlorine, nothing happens, but if we add this catalyst, then we get substitution. Nitric acid is the active nitrating agent, but again, the activation energy is too high, so we have to add sulfuric acid. Let's see, we didn't talk about these reactions. We'll go into more detail about those today. Okay, this is the general reaction for electrophilic aromatic substitution. Okay, so here's, I'm going to show you this again. This is chlorination. Okay, so chlorine attacks the iron 3 chloride or ferric chloride. Okay, Okay, and then this generates the electrophile Cl+, and the counter ion is FeCl4-. Okay, the Cl+ is what the benzene ring attacks. Okay, so we get this familiar intermediate. We're going to see something like this in all of these substitution reactions. And then chloride pulls away from the iron. It takes that H. Okay, that restores the benzene ring. We get chlorobenzene. We get HCl gas as a byproduct. And by definition, a catalyst is unchanged at the end. Okay, so we get our iron 3 chloride back. Bromine and iron 3 bromide reacts exactly the same way to give us bromobenzene. Okay, here's nitration. All right, so nitric acid actually acts as a base here. It picks up a proton from sulfuric acid. All right, this intermediate has two positive charges next to each other. Okay, if you draw out the full Lewis structure, you see that. And so water quickly gets kicked out. Okay, to have two like charges next to each other is very unfavorable. Okay, so water gets kicked out. Now we've got our electrophile, NO2+. Okay, it's well known that NO2+ is the electrophile from certain chemical companies like Sigma Aldrich. You can buy nitronium salts. Okay, but this is a convenient method of generating nitronium in the laboratory by mixing nitric and sulfuric acids. Okay, so the benzene ring attacks a nitronium ion, water takes that hydrogen, and our product is nitrobenzene, okay, which is shown here. All right, the Friedel-Crafts alkylation forms a new carbon-carbon bond between an aromatic ring and an alkyl group. The Friedel-Crafts reaction actually has been in use for a long time. It was discovered back in the late 1800s, and it was actually developed independently by two chemists. Friedel was in France, Crafts was an American. They developed this independently about the same time. And it's a method of producing alkyl substituted benzenes. Okay, so the usual method, this is not the only way, but this is probably the most common method. And that is to start with an alkyl chloride and use a catalyst, aluminum chloride. Aluminum is a very good electron pair acceptor. Okay, not only is there a large difference between chlorine and aluminum as far as electronegativity, these chlorines are pulling electron density away from the aluminum. Aluminum doesn't have an octet. Okay, there's no lone pair. It only has 6 valence electrons. And so it's very prone to accepting a pair of electrons because that gives it an octet. Okay, so chlorine donates a pair of electrons to aluminum. Okay, we have this heterolysis step, and we generate a carbocation, which is the electrophile. Okay, so once we get that electrophile, okay, this shows the resonance stabilized sigma complex, as it's called. Okay, and then aluminum chloride dissociates. Okay, this probably looks very similar to the chlorination we saw a few minutes ago. chlorine pulls away, grabs that hydrogen, and this pair of electrons in this bond moves toward the positive charge. So we get our alkyl benzene. Okay, so some of the limitations of Friedel-Crafts alkylation. Okay, it's only practical with stable carbocations, such as secondary and tertiary. Okay, because these can rearrange. You can still make toluene or ethylbenzene using Friedel-Crafts. Because it goes through a carbocation, these carbocations can rearrange, and so you may not get the product you're expecting. Okay, it also does not work at all if the benzene rings also bear one of these strongly electron withdrawing groups. Okay, so if any of these groups are also present on the benzene ring, okay, it won't work. What are the characteristics? Okay, notice here we've got several that have a carbonyl group next to the ring, a CO double bond. The sulfonic acid group is strongly electron withdrawing. The nitrile group, nitro is very strongly electron withdrawing. This one has a plus charge, so it's going to withdraw electrons out of the ring. Same way with CF3 and CCl3. So if any of these groups are present, the reaction just won't work. Okay, so this is a variation of the Friedel-Crafts. This is called the acylation, and this results in a phenyl ketone or an acyl benzene. Okay, so we start out again. Aluminum chloride is our catalyst, and we'll use an acyl chloride. Okay, this is like a carboxylic acid, except we've replaced the OH here with a chlorine. And the net result is we get this ketone, we get HCl gas, we get our catalyst back. Right, this occurs by very similar mechanism. All right, chlorine uses a pair of electrons to attack the aluminum. We have a dissociation. And then we have what is called the acylium ion, where we have a CO double bond, a plus charge on the carbon. This is stable because its resonance is stabilized by resonance. The oxygen can also carry the plus charge. Okay, I'm going to go ahead and finish this up. So we have our acylium ion. Benzene ring attacks the carbon. We get this familiar intermediate. The adjacent position will carry a plus charge. Aluminum chloride. will dissociate. It will remove this hydrogen. Get this phenyl ketone plus HCl gas, and then we get our catalyst back. Okay, there are other ways of generating a carbocation. One is to use an alkene and a strong acid like sulfuric or phosphoric. Okay, remember Markovnikov's rule, the rich get richer, so carbon number 1 gets the hydrogen, which places a plus charge on carbon number 2. Benzene ring attacks carbon number 2, so that's why we get isopropyl benzene and not propylbenzene. Okay, here's tert-butyl alcohol. Okay, again, this will generate a carbocation. Oxygen will pick up an H from phosphoric acid. Water leaves, that gives us a tert-butyl carbocation. Benzene ring attacks that. Water removes the adjacent hydrogen, and then we get tert-butyl benzene. Okay, next we're going to look at orientation and rate when it comes to benzene derivatives and electrophilic substitution. Right, so far, we've just been looking at reactions involving benzene. What if there is already a substituent on the benzene ring and we're doing a reaction to put another substituent on there? Okay, again, we want to consider orientation and rate. Okay, some substituents that are already present will speed up the reaction relative to benzene. Some will slow it down. Some will slow it down very greatly. And then orientation. Where does that second substituent that we're putting on, where does it go relative to the first? Okay, it depends on what the original substituent was. Okay, so we have what are called ortho-para-directors, and then we have meta-directors. And then we have groups that are activating and others that are deactivating. Okay, this was implied earlier. Okay, back here. Okay, when we're doing the Friedel-Crafts, if any of these groups are already present, these are so deactivating that the Friedel-Crafts won't work. Okay, with other substitution reactions, we can do substitutions on deactivated rings, but they occur much more slowly. Right, so this is anisole or methoxybenzene. Okay, and notice here it says the bromination of anisole proceeds many times faster than the bromination of benzene. Okay, notice that we don't even need a catalyst. Okay, you add bromine and this reaction will occur fairly quickly. We get two products, the O-bromoanisole or 2-bromoanisole and the 4. So this is what's called an ortho-para-director. Okay, we don't see the 3-bromoanisole. Okay, acetic acid is a solvent, it's not a catalyst. Okay, the nitro group is a strong deactivator, and it's also what's called a meta-director. Okay, so the major product here is M-dinitrobenzene or 1,3-dinitrobenzene. That occurs at 93% yield. Okay, the other two isomers are less than 7% combined. Notice the conditions here. This takes place at 100 degrees Celsius. Okay, if you're nitrating benzene, okay, you would usually do that in the laboratory at 0 degrees. You'd put it in an ice bath. Okay, so that's how much slower nitrobenzene reacts than benzene. So it's a deactivator, and it's also what we call a meta-director. Okay, here's a summary of several substituent groups. Okay, up at the top, we have what we call strongly activating. Okay, if we have aniline or a substituted aniline or a phenol or a phenyl ether. Okay, notice what these have in common is they have a lone pair on the atom next to the ring. Okay, so those are strongly activating, okay, which means that phenol or aniline would react much faster than benzene. These are moderately activating. Okay, they don't have the carbonyl next to the ring, but rather they have an N or an O with lone pairs next to the ring. Okay, and then an R group or a benzene ring are weakly activating. Okay, so toluene or ethylbenzene would react a little bit faster than benzene. Okay, halogens that are present, these would slow down the reaction a little bit. These would slow it down more. Okay, these ones that have the carbonyl next to the ring, and also the sulfonic acid group. And then these are strongly deactivating. Nitro, anything with a plus charge on the nitrogen, CF3, CCl3. Okay, all of the activators are orthopara-directors. All of the deactivators are meta-directors except the halogens. The halogens are deactivating, but they're orthopara-directing. Let me repeat that. All of the activators are orthopara-directors. All of the deactivators are meta-directors except the halogens, which are orthopara-directors. Okay, so some generalizations. Let's see, I have about 1 minute remaining. I'm going to go ahead and stop here, and we'll pick this up next time.